Hi again, everybody. Welcome back. At this point in this chapter on rotational kinematics, we have talked about how the equations for one-dimensional kinematics are very, very similar to rotational kinematics. In fact, they're almost exact copies of each other, just using different symbols. So we have a couple of kinematic values right here that we want to be able to solve for. Part A asks us for the angular acceleration, so we're solving for angular acceleration here. And part B, well, it doesn't say part B, but it says how many revolutions does the ball make. So that is actually a certain number of, that's a certain angular displacement, or theta. All right, so that's our alpha right there, and this is our theta, and we have equations that solve for that. All right, well, let's go ahead and read it. To throw a curveball, a pitcher gives the ball an initial angular speed of 36.0 radians per second. Okay, so that is our, I call it omega initial instead of omega O right there. And that is 36.0 radians per second. Okay? Time, the amount of time that elapses. Now, this is not period. Period, remember, is the amount of time it takes for an object to rotate one time. This is obviously several rotations later. So it's the amount of time, 0.595 seconds later. So half a second later. Its angular speed is decreased. So it is our omega final, 34.2 radians per second. All right, so we want to solve for our alpha, our angular acceleration, and we want to solve for our theta. All right, now I'm afraid that I'm going to start running out of space right here if I don't do something about this. So I'm going to shrink this all down a little bit right here and give us a little bit more working room. Okay. Well, as you may recall that I said several times in kinematics, if you have three knowns, whether it's displacement, acceleration, velocity, final velocity, time, etc., usually you can solve for pretty much anything. There's going to be an equation for that, for those knowns right there. So for part A, we are solving for the angular acceleration. All right, and so that means that we need an equation that has initial angular velocity, time, and final angular velocity. And I think we do have an equation for that. It goes like this. Final angular velocity equals initial angular velocity plus angular acceleration, I should say, times time. So let's just turn that around and solve for our angular acceleration. Our angular acceleration is going to be what we subtract over our omega initial, right? So angular velocity final minus angular velocity initial, and divide that then by time. And we have values for angular acceleration. By the way, are we going to predict this acceleration, this angular acceleration, is going to be positive or negative? Again, assuming these initial velocities here are angular velocities are positive, which they are. They're in the counterclockwise direction. Well, if it's slowing down, then we should expect that acceleration is going to be negative, right? Let's try it out. Final angular velocity is 34.2 minus our initial, which is 36. Yep, that's going to be negative, divided by the amount of time, 0.595 seconds, and that gives us an angular acceleration of negative 3.03 meters per second squared. No, radians per second squared, right? Radians per second squared, and that is our alpha. That's our angular acceleration. All right, let's go ahead now and solve. It doesn't say part B, but I'm calling it part B for our angular displacement. All right, how many radians around has it gone in that amount of time? Well, we have one more value to work with. We have acceleration here, but let's see if we can find an equation that that uses just what we were given right here. Our initial angular velocity, time, and our final angular velocity. What do we have? Well, we have an equation. In fact, to save space, I'm going to write it over here for angular displacement. We have our final angular position equals our initial angular position plus 1/2 times we're really saying the average angular velocity. So the omega final plus omega initial times time. Okay, this is our average angular velocity right here in that amount of time. You add two things and divide them by 2. That's your average. So that's your average angular velocity times time, and you add that to your initial position right there. Well, we're going to assume our initial angular position is 0. It's starting at no radians. It hasn't rotated at all before he throws it. So we're really going to take this side and just turn that into delta theta. All right, delta theta equals 1/2 times the final angular velocity plus the initial angular velocity, all multiplied by time. All right, that's going to be our equation that we can use to solve for our total angular displacement. All right, so delta theta total is 1/2 times what's our final angular angular velocity? That is 34.2. Plus our initial angular velocity is 36.0 times, I don't need a parenthesis right there, 0.595. I do, however, need more space. It's getting a little tight in there. I think we're okay. All right, let's find out what the total angular displacement was. How many radians that ball actually went and spun through by the time it kind of decreased to that final angular velocity. What do we get? All right, and if my calculations are right, I get that our change in angular displacement is 20. Let's see how many sig fig. 3. 20.9 radians. All right, so we know that there's about 6.28 radians in one revolution, so that 6.28 goes into 20 about 3 times, so it must have spun about 3 times by the point that it slowed down to that final angular velocity. Okay, so again, a very, very close relationship, a close parallel to our values in one-dimensional kinematics, but we have our radians instead of meters, and radians per second and radians per second squared, but everything else matches up very, very nicely. So that's example 10.5, finding angular acceleration and finding angular displacement. Thanks. I'll see you on the next one.